Black holes are some of the most mysterious objects in the universe. They have the power to bend space, trap light, and challenge our very understanding of physics. But what if black holes are more than just cosmic destroyers? Some scientists suggest they could be the birthplace of entirely new universes. In this video, we'll explore the fascinating idea that our own universe might have been born from a black hole. Imagine pointing a flashlight into a dark room and watching the beam disappear into a corner it can never leave. A black hole is something like that corner for light, a region of space where gravity is so strong that nothing, not even light, can escape. That simple sentence captures the core idea. Black holes are places where gravity has won so decisively over everything else that escape becomes impossible. But there's a lot more to understand behind that statement. Black holes are not mysterious monsters hiding in the dark. They are the natural consequence of the laws of gravity and matter, and they reveal extreme regimes where our best theories get pushed to their limits. At the heart of the black hole idea is gravity's ability to pull matter together. In ordinary life, gravity keeps your feet on the ground and the Earth in orbit around the sun. Under most circumstances, other forces, the pressure from hot gas inside a star, the electromagnetic forces that keep atoms from collapsing, and quantum effects, push back against gravity. But if you take enough mass and pack it into a small enough volume, gravity can overwhelm those opposing forces. The defining moment for a black hole is when the mass is concentrated inside a sphere whose radius is smaller than a critical size called the Schwarzschild radius. For any given mass, that radius is the distance within which escape velocity equals the speed of light. Cross that boundary, and you're in a region from which escape is impossible. The Schwarzschild radius gives a concrete way to picture how black holes scale. For an object with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. So if the Sun were compressed to a ball 3 kilometers across, far smaller than the Sun's current radius of about 700,000 kilometers, it would become a black hole. Scale that up. A 10 solar mass black hole would have a radius of roughly 30 kilometers. A supermassive black hole of 1 billion solar masses has a Schwarzschild radius measured in billions of kilometers, comparable to the size of our solar system. The size people often imagine for a black hole is proportional to its mass. Doubling the mass doubles the radius. But the more massive ones can be enormous in sheer scale, even though, in terms of density, the picture can be surprising. Some supermassive black holes have average densities lower than water because the volume inside their event horizon grows faster than mass. Two features are commonly mentioned when describing a black hole's structure: the event horizon and the singularity. The event horizon is the boundary, the point of no return. It's not a material surface you can touch. Rather, it's a location in space where the escape velocity equals the speed of light. Crossing the event horizon means all future paths, all possible directions that an object could move in time, lead further inward. From the perspective of someone falling in, the event horizon is uneventful. You wouldn't feel a sharp wall. But to an outside observer watching you approach the horizon, strange things happen. Your image appears to slow down, become increasingly redshifted, and fade away, never quite reaching the horizon in finite external time. That odd behavior arises because of how spacetime is curved by the black hole and how signals take longer and lose energy climbing out of its gravity well. The singularity is the other commonly discussed part. In the simplest mathematical black hole models, like those first calculated by Carl Schwarzschild, the singularity is a point, or for rotating black holes a ring, at the center where densities and gravitational tidal forces become infinite, and where the equations of general relativity break down. That infinity signals not a physically meaningful place, but a limit where our current theory stops being reliable. Most physicists expect that quantum gravity, a future theory combining quantum mechanics and general relativity, will replace the classical singularity with some new description that avoids infinities. Until then, it's fair to say the singularity is the best way our equations currently describe the black hole's core, a region where space and time as we know them cease to behave normally. How do black holes form? The most familiar route is the collapse of massive stars. A star is a battle between gravity pulling inward and pressure from nuclear fusion pushing outward. In stars like the Sun, fusion of hydrogen into helium provides that outward pressure for billions of years. In much more massive stars, those with more than about 8 times the mass of the Sun, nuclear fusion proceeds through heavier elements until a core of iron forms. Iron cannot yield energy through fusion, so once you have a substantial iron core, the outward pressure falters. If the remaining outward forces cannot support the core's mass, the core collapses. For many massive stars, the collapse is stopped by quantum degeneracy pressure, the same principle that holds up white dwarfs, electron degeneracy, or neutron stars, neutron degeneracy. If the remaining mass after a supernova explosion is larger than about 2 to 3 solar masses, the precise limit is not known exactly and depends on the details. Even neutron degeneracy pressure cannot halt collapse, and the core continues compressing to form a black hole. It helps to picture this by thinking about balloons and rubber bands. A star is like an inflated balloon held open by heated air, pressure from fusion. If the air cools and the balloon wall cannot resist the pressure change, the balloon collapses. In a real star, cooling corresponds to the end of fusion. The change in internal reactions leaves nothing to resist gravity. What follows is dramatic. Material falls inward at a sizable fraction of the speed of light, often rebounding in a supernova explosion that can outshine an entire galaxy for weeks. Whether a black hole forms depends on the dance between the collapsing core and the outer layers. If enough mass remains or falls back, the core can cross the threshold and vanish behind an event horizon. Black holes come in a variety of sizes. The 2 most prominent classes are stellar mass black holes and supermassive black holes. Stellar mass black holes form from individual stars and typically range from a few to tens of times the Sun's mass. These are often found in binary systems, where matter siphoned from a companion star forms a hot, luminous accretion disk around the black hole, producing strong X-rays that we can detect. Supermassive black holes, millions to billions of times the Sun's mass, sit at the centers of most galaxies, including our own Milky Way. Their formation is less straightforward. They might grow by repeated mergers of smaller black holes and by accreting gas over billions of years. Or perhaps some formed directly from the collapse of enormous gas clouds early in the universe's history. There's increasing evidence for intermediate mass black holes too, a bridge between stellar and supermassive, though those are harder to find and still subject to active research. One of the most striking things about black holes is how they interact with their surroundings. Despite the name, black holes can be among the brightest objects in the sky when surrounded by gas. Matter spiraling into a black hole doesn't fall straight in. It tends to form a disk, known as an accretion disk, where friction and magnetic effects heat the gas to enormous temperatures, causing it to glow in X-rays and sometimes visible light. The efficiency of converting mass to energy in an accretion disk can be much higher than nuclear fusion. That's why supermassive black holes powering quasars can outshine entire galaxies. The gravitational energy released by material falling into them is immense. These accretion disks can also launch beams of particles at nearly the speed of light, known as relativistic jets. The exact mechanism that forms jets is complex and still an active area of research, but magnetic fields twisting and being dragged by the spinning black hole and its disk play a central role. These jets can travel for hundreds of thousands of light years and inject energy back into the galaxy. influencing star formation and the evolution of galactic structure. Gravity near a black hole becomes so strong that it produces effects with no everyday analogs. Tidal forces, differences in gravity from one side of an object to another, become extreme. If you fall feet first into a small, stellar mass black hole, the gravitational pull on your feet will be stronger than on your head, stretching you into a long, thin shape in a process colloquially called spaghettification. For supermassive black holes, the event horizon is much larger and tidal forces at the horizon can be relatively small. You might cross the horizon with no dramatic stretch and be unaware of anything special until deeper inside. Time also behaves oddly. Clocks near the black hole tick more slowly compared to those far away. To an outside observer, a falling astronaut seems to slow down near the event horizon and never quite cross it. The astronaut, however, experiences time normally and crosses the horizon in finite proper time. Light itself is affected in dramatic ways. A black hole bends light paths around it. If you orbit far enough away, light can circle the black hole in what's called a photon sphere. That bending creates gravitational lensing effects. The black hole can magnify and distort images of objects behind it. The first direct picture of a black hole's surrounding emission, released in 2019 by the Event Horizon Telescope, showed a ring of light surrounding a dark shadow. The dark region is the silhouette of the event horizon against glowing hot gas, and the ring is light bent and brightened by the black hole's gravity. That image provided strong visual evidence that the object is indeed a black hole and aligned beautifully with predictions from general relativity. Another remarkable avenue of discovery in recent years has been gravitational waves. When two black holes spiral together and merge, they send out ripples in spacetime, tiny stretching and squeezing of distances that race outward at the speed of light. Observatories like LIGO and Virgo have detected many such mergers. These signals carry information about the masses and spins of the black holes involved, and have confirmed that black holes of various masses exist, and that they can indeed merge. The gravitational wave detections were a monumental confirmation of Einstein's theory and opened a new window onto the universe, one that listens to the cosmos rather than watching it. An important nuance to make clear is that a black hole is defined entirely by a few properties visible from the outside: its mass, spin, how fast it rotates, and electric charge. In fact, astrophysical black holes probably have negligible net electric charge, because any charge would attract opposite charges from the surrounding plasma and neutralize quickly. Spin matters a lot because a rotating black hole drags spacetime around with it, an effect called frame dragging, which changes how matter behaves nearby, influences the inner edge of accretion disks, and can help launch jets. In physics, the principle that black holes have no hair is a playful way of saying black holes are simple objects whose external description is remarkably sparse. Despite whatever complicated stuff collapsed to make them, what remains for outside observers can be described with just mass, spin, and charge. If you want to imagine what falling into a rotating black hole might be like, think of a whirlpool in water. The faster the whirlpool spins, the more it drags objects around it. A rotating black hole drags space itself in this way, making orbits and light paths behave in asymmetric ways. This frame dragging also introduces structures like the ergosphere, a region just outside the event horizon where it's impossible for an object to remain stationary relative to distant stars. Everything there is compelled to co-rotate with the black hole to some extent. The ergosphere is where some theorized mechanisms can extract energy from a black hole's rotation, essentially tapping into its spin. We should also address a few common misconceptions. First, black holes aren't cosmic vacuum cleaners that roam galaxies gobbling up everything in their path. To an object at a safe distance, a black hole's gravity is the same as any other mass of the same size. If the Sun were magically replaced by a black hole of equal mass, the Earth would continue orbiting as if nothing had changed. We'd lose sunlight but not have our orbit altered. Second, black holes can't be seen directly because light doesn't escape from inside the event horizon. What we observe are indirect signs: the motion of nearby stars, X-rays from heated accreting gas, jets, and gravitational waves from mergers. There's also a fascinating quantum twist. In the 1970s, Stephen Hawking showed that black holes are not entirely black when quantum effects are taken into account. Particle-antiparticle pairs are constantly being created and destroyed even in empty space. Near an event horizon, one of these particles could escape while the other falls in, which, when analyzed carefully, results in the black hole emitting a faint thermal radiation, now called Hawking radiation. This radiation implies that black holes have a temperature and gradually lose mass over extremely long timescales, eventually evaporating. For astrophysical black holes, however, the Hawking temperature is so low that the evaporation time far exceeds the age of the universe. Only tiny black holes, far smaller than any we expect to find naturally, would evaporate on observable timescales. Nonetheless, Hawking radiation has enormous conceptual implications because it ties gravity and quantum mechanics together and leads directly to the black hole information paradox. The information paradox arises from the apparent contradiction between quantum mechanics, which preserves information, and the suggestion that information about matter falling into a black hole might be lost forever as the black hole evaporates. If information is truly lost, it would break the rules of quantum theory. Physicists have proposed many ideas to resolve the paradox. Maybe information is encoded in the Hawking radiation in subtle ways. Maybe it is stored on the event horizon itself in what's called holographic principles. Or perhaps quantum gravity leads to structures, wormholes, firewalls, or other exotic phenomena that change our picture. There is no consensus yet, but progress in theoretical physics, especially in string theory and studies of black hole thermodynamics, suggests that the paradox points toward deep and fundamental insights about how space, time, and information are related. Why do researchers find black holes so exciting beyond their obvious drama? Because they are natural laboratories for the extreme. They concentrate mass and curvature into small regions, providing conditions where general relativity and quantum mechanics must meet. Observations can challenge and refine our theories. When the Event Horizon Telescope imaged the shadow of the supermassive black hole in the galaxy MADI 7, and when LIGO detected gravitational waves from black hole mergers, those were triumphs of theoretical prediction meeting experimental achievement. Each new observation helps rule out possibilities and sharpens our understanding. Black holes also matter on grander cosmic scales. Supermassive black holes influence the growth and structure of galaxies. The energy and jets they inject can regulate star formation and shape the gas distribution in galaxy clusters. There's a surprising correlation between the mass of a galaxy's central black hole and properties of the galaxy's bulge, hinting that black hole growth and galaxy evolution are interconnected. These relationships are active areas of research and help us understand how the large-scale structures we see today came to be. There are still many mysteries. How did the first supermassive black holes grow so massive so quickly in the early universe? What exactly happens inside the event horizon and at the singularity? Do primordial black holes from the early universe exist, and could they contribute to dark matter? Can we detect signatures of quantum gravity in gravitational waves or in precise imaging near the horizon? New telescopes, longer gravitational wave observations, and more detailed simulations will keep pushing these questions forward. It's also worth thinking about scales and time. Black hole processes can be both rapid and glacial. A black hole merger detected by LIGO has a dramatic chirp lasting seconds, while an accretion disk and jet from a supermassive black hole can persist and evolve over millions of years. Black holes don't suck indiscriminately, but anything that crosses the event horizon is lost to outside view. The black hole grows and stores that mass energy in a way described by its external properties. Over unimaginably long timescales, Hawking radiation suggests even black holes will fade. Although objects like supermassive black holes will outlive any human timescale by orders of magnitude. Thinking pragmatically, how do astronomers find black holes? The methods vary by mass and context. For stellar mass black holes, one of the earliest and most reliable ways is to look for a companion star whose motion betrays the presence of an unseen massive partner. Measurements of orbital motion can reveal the mass of the invisible object. If it exceeds the maximum mass for a neutron star, you have a strong black hole candidate. X-ray astronomy also plays a crucial role. When a black hole accretes matter from a companion or interstellar gas, the infalling material heats up to emit X-rays that telescopes like Chandra and XMM Newton detect. For supermassive black holes, astronomers study the motions of stars and gas near galactic centers. The orbits of stars near the Milky Way's center, tracked over decades, have provided strong evidence that a compact object of about 4 million solar masses, called Sagittarius A, resides there. Radio imaging, spectroscopy, and now horizon-scale imaging with networks of telescopes have all offered complementary views. As we push the boundaries of observation, new tools change the game. The Event Horizon Telescope's image relies on a technique called very long baseline interferometry, which links radio telescopes around the Earth to achieve the resolution needed to see structures the size of a black hole's shadow. Gravitational wave observatories listen for ripples in spacetime from compact object mergers, complementing electromagnetic observations. Future instruments, like space-based gravitational wave detectors and more sensitive telescopes across the spectrum, promise to reveal more about black hole populations and behaviors. Beyond astrophysics, black holes have inspired thinking in many areas of physics and philosophy. They force us to confront what we mean by space and time. They raise questions about determinism and information. They serve as testing grounds for ideas about entropy, temperature, and quantum field theory in curved spacetime. Even practical concepts like how to extract energy from a rotating object find a surprising analog in theoretical processes involving black holes. At the everyday level, black holes also make for great metaphors and cautionary reminders. Their simplicity, being described by so few parameters, juxtaposed with the complexity of their surroundings, tells us something profound about how nature organizes itself. Simple underlying laws can lead to rich phenomena. At the same time, the limits of our understanding at singularities remind us that science is ongoing. Theories are tools that work within domains and must be replaced or extended when they hit their limits. If you ever feel a little overwhelmed by the extreme scales and abstract physics, it helps to bring things back to relatable experiments. Imagine spinning a ball in syrup. The syrup represents spacetime being dragged around by a spinning mass. Near the ball, the syrup moves with it, affecting how smaller objects in the syrup move. Or picture a heavy marble on a stretched rubber sheet. Set the marble in the middle and watch other marbles spiral toward it in curved paths. That's the familiar visualization of mass curving spacetime. None of these analogies captures every aspect of a black hole, but they provide intuitive footholds. Finally, why should anyone care? Because black holes are both spectacular and instructive. They are cosmic laboratories that test the extremes of physics, engines that power some of the brightest phenomena in the universe, and clues about the deep structure of reality. Their study has led to new ideas, technologies, and ways of thinking about the universe. From the calm orbit of a star that hints at a hidden giant to the short burst of gravitational waves announcing two black holes merging, they tell us stories about origins, dynamics, and the limits of knowledge. Black holes are not the end of the story but a beginning, places where familiar rules bend and new principles emerge. They remind us that the universe often refuses to be simple and that pushing into extremes is how we learn. Whether you're watching a simulation of a glowing accretion disk, tracking how a companion star wobbles, listening to the chirp of colliding black holes, or pondering the fate of information swallowed by an event horizon, you're participating in the scientific adventure. The more we observe and the more our theories evolve, the clearer the picture becomes, not complete, but richer and more fascinating than ever. Black holes are both a testament to humanity's curiosity and a gateway to the deeper physics that lies ahead. Imagine you could keep squeezing a lump of stuff, an apple, a car, a mountain, smaller and smaller. At first, nothing dramatic seems to happen. Atoms get closer, the air is pushed out, maybe it heats up a bit, but keep compressing. Eventually, you reach scales where the normal forces that hold matter up start to fail. This is the step-by-step story of gravitational collapse. What happens when gravity wins and matter is crushed to the limits of physics as we know it? The end point that general relativity points to is called a singularity, but that word hides an important point. Singularity is less a clean, physical object and more a flashing red light on our equations that says, we ran out of tools here. To understand how matter resists compression, it helps to think about the everyday sources of pressure. An ordinary gas resists being squeezed because its particles bounce off each other and the walls of their container. That bouncing creates pressure. In a star, thermal pressure from nuclear fusion fights gravity. When fuel runs out, the central pressure drops and the star starts to contract under its own weight. For many objects, there are special quantum effects that can stop collapse before anything mysterious happens. Electrons, for example, obey a rule called the Pauli exclusion principle. No two electrons can occupy exactly the same quantum state. Picture a bus with individually numbered seats. Once the easy seats are taken, new passengers have to take higher energy seats. When a star's core shrinks and electrons are squeezed closer, this stacking of electrons into available states creates a powerful form of pressure called electron degeneracy pressure. That pressure can hold up objects up to a certain mass. White dwarfs, the leftover cores of stars like our Sun, are stabilized by this electron degeneracy. But there's a catch. There is an upper mass limit, known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. If the core's mass exceeds that, electron degeneracy can no longer hold off gravity and collapse continues. When electrons get crammed so tightly that they are forced into higher energy states, they can combine with protons to form neutrons, releasing neutrinos in the process. This is what happens during the core collapse of a massive star that triggers a supernova explosion. The result can be a neutron star, a city-sized object with a mass greater than the Sun, held up by neutron degeneracy pressure and strong nuclear forces. Neutron degeneracy is like electron degeneracy, but with neutrons playing the role of the stacked passengers. Neutron stars are among the densest stable forms of matter we know. A teaspoonful of neutron star material would weigh billions of tons on Earth. Even neutron degeneracy has a limit. Above a certain mass, the Tolman-Oppenheimer-Volkoff limit, which is uncertain but likely a few times the Sun's mass, not even neutron pressure plus the strong nuclear force can resist gravity. The core collapses further and, according to general relativity, a black hole forms. A black hole is not just an extremely compact object. It's a region where gravity is so strong that nothing, not even light, can escape from within a boundary called the event horizon. Outside observers see the horizon as the dividing line between what can and cannot influence the rest of the universe. A common misconception is that the event horizon is a physical surface like the skin of a balloon. It isn't. If you fall through the horizon of a sufficiently large black hole, you wouldn't feel a sudden jolt at that exact moment. The horizon is a point of no return defined by causal structure, not a tangible barrier. For a stellar mass black hole, tidal forces near the horizon can be fatal long before you notice anything special at the horizon. For a supermassive black hole, the tidal forces at the horizon can be small enough that you cross it without immediate sensation. Where things become truly dramatic is deeper inside, according to classical general relativity. General relativity describes gravity as the curvature of spacetime produced by mass and energy. When a massive object collapses, it warps spacetime more and more. If the collapse is allowed to continue unchecked, the curvature becomes arbitrarily large in a region of spacetime. In Einstein's equations, this shows up as quantities blowing up to infinity, which is what physicists call a singularity. Penrose and Hawking formalized this idea with singularity theorems in the 1960s and 70s. Under very general conditions, reasonable energy conditions, trapped surfaces, causality assumptions, gravitational collapse inevitably leads to geodesic incompleteness, which is the technical way of saying there are paths in spacetime that end abruptly in finite proper time. Put plainly, classical relativity predicts that there are situations in which the equations stop making sense because physical quantities become infinite. But infinite in physics is almost always a sign that the theory has been pushed past its domain of validity. When you get to lengths and energies where quantum effects of gravity should matter, typically around the Planck scale, which is tiny, about 10⁻35 meters, you can no longer trust a theory that ignores quantum behavior. That's why many physicists interpret the singularity not as literal infinite density matter sitting at a point, but as a symptom that general relativity must be replaced by a quantum theory of gravity in those regimes. One way to picture this is to think of a map that becomes meaningless when you zoom into atomic scales. The map's lines might look infinitely thin and the scale breaks down. You wouldn't expect a subway map to tell you about the quantum states of electrons. Similarly, Einstein's smooth spacetime picture likely needs a different description at the smallest scales. So what happens to the singularity in a quantum theory of gravity? Several competing ideas offer different answers, and they make distinct predictions that, in principle, could be tested. One class of ideas suggests the singularity might be replaced by a bounce. In loop quantum gravity, for instance, the quantization of spacetime leads to a repulsive effect at extremely high densities that could halt collapse and reverse it, creating a Planck star or a transition to an expanding phase. In this picture, the black hole might eventually release its contents in a white hole-like explosion, but the timescales involved can be enormous or context-dependent. Another idea comes from string theory. The fuzzball proposal says that what we think of as a black hole is actually a tangle of strings and brains spread out to roughly the would-be horizon scale. There is no singular point at the center. Instead, the interior is replaced by microstates of the strings. Each of these pictures tries to avoid the literal infinities of classical gravity by introducing new physics. Then there are more conservative possibilities. Maybe the singularity remains a place where densities become arbitrarily large, but quantum effects smear out the infinities in ways that still leave a compact, possibly highly scrambled core. Or possibly, under certain conditions, regions of extreme curvature could be exposed to the outside universe as naked singularities, points of infinite curvature not hidden behind a horizon. However, most physicists think naked singularities should be forbidden because they would break determinism. If the laws of physics produce an unpredictable infinity visible to the rest of spacetime, predictive power vanishes. Roger Penrose conjectured a cosmic censorship principle that forbids naked singularities under generic circumstances, but it remains a conjecture, not a proven theorem. Numerical experiments and analytical studies show both encouraging and troubling examples. The question remains open and is part of ongoing research. What does an observer outside a collapsing star actually see? From far away, the collapse appears to slow down as the stellar material approaches the event horizon. Light that escapes from just outside the horizon is redshifted, its wavelength stretched to longer, redder values, so signals take longer and longer to reach you and become fainter and lower in energy. In practice, after a short time, the collapsing object becomes effectively invisible, appearing to freeze near the horizon and fade away due to extreme redshift. That doesn't mean the horizon isn't formed. An observer falling with the matter crosses the horizon in finite proper time and eventually encounters whatever fate awaits inside. Gravitational waves, ripples in spacetime produced by accelerating masses, have opened a remarkable new window on gravitational collapse. The LIGO and Virgo observatories have detected signals from binary black hole mergers and neutron star collisions. In these events, two compact objects inspiral, merge, and settle into a single remnant. The final phase, called ringdom, carries information about the newly formed object's spacetime geometry. So far, the observed ringdoms match the predictions of classical black hole models in general relativity to good precision, reinforcing the idea that horizons and compact interiors behave as GR describes, at least outside the horizon. But gravitational wave detectors are rapidly improving, and some researchers are looking for subtle deviations. Echoes in the ringdom signal, anomalous time delays, or other signatures that might hint at modifications near the would-be horizon or at the absence of a true singularity inside. Black hole imaging has also progressed. The Event Horizon Telescope produced the first horizon-scale image of the supermassive black hole in the galaxy MADI 7 and later of Sagittarius A at the center of our galaxy. Those images capture the silhouette cast by the black hole's strong gravity on the surrounding hot plasma. While they don't show the singularity, which lies well inside, they do confirm the existence of the event horizon scale shadow and test GR's predictions in the strong field regime. Future, more detailed images and time-variable studies of accretion flows may help weed out exotic alternatives to classical black holes, or provide constraints on how matter behaves near the horizon. Hawking discovered that black holes are not completely black. Quantum field theory in curved spacetime shows that black holes emit thermal radiation, now known as Hawking radiation, with a temperature inversely proportional to their mass. For astrophysical black holes, this temperature is incredibly tiny, far colder than the cosmic microwave background, so Hawking radiation is negligible in everyday astrophysics. But over unimaginably long timescales, Hawking evaporation implies that black holes can lose mass and eventually disappear. This leads to the information paradox. If matter carrying quantum information falls into a black hole that then evaporates thermally, where does the information go? Pure thermal radiation seems to destroy the information about the initial state, which would violate quantum mechanics' rule that information is preserved in time. Resolving this paradox motivated years of work and key developments like the holographic principle and the ADS/CFT correspondence, which suggest that in some contexts, information is preserved and the black hole's interior is encoded in degrees of freedom on its boundary. The details remain fiercely debated, but the debate has pushed deeper understanding of how gravity and quantum mechanics interplay. Another twist in the story comes from the thermodynamic analogy. Black holes have entropy proportional to the area of their horizon, not their volume, as shown by Bekenstein and Hawking. That was surprising at first. Entropy is usually an extensive quantity that scales with volume. The area scaling hinted at a deeper principle, that the number of microscopic states of a gravitational system might be encoded on a lower dimensional surface. This idea underlies the holographic principle and has profound implications for how we think about space itself. Perhaps spacetime and gravity are emergent, arising from more fundamental quantum degrees of freedom described in fewer dimensions. There's also a cosmic angle. The Big Bang is often described as a singularity in the past. Tracing the universe backward in time, densities and temperatures rise without bound in classical cosmology, culminating in a point where the equations blow up. Again, physicists generally expect that quantum gravity will smooth out or replace this classical singularity, perhaps leading to a bounce or a pre-Big Bang phase. Proposals like loop quantum cosmology suggest the Big Bang could have been a big bounce, with a contracting phase preceding our expanding universe. Other ideas propose that singularities are never truly reached because some new physics intervenes. These alternatives are still speculative but cosmological observations. For instance, of primordial gravitational waves or subtle features in the cosmic microwave background, might someday provide clues. What's remarkable about singularities is that they sit at the crossroads of gravity, quantum mechanics, thermodynamics, and information theory. The simple question of what happens when matter is compressed to its limit forces us to confront deep puzzles. What are the true microscopic degrees of freedom of spacetime? How is information stored and transformed in extreme gravity? Are space and time fundamental or emergent from something more primitive? It's not just a technical problem, it's a conceptual one that may reshape our picture of the universe. At the same time, there are practical observational constraints. If singularities were visible to the outside world, naked singularities, they might produce dramatic signals, unusual lensing patterns, bursts of high-energy radiation, or distinct gravitational wave signatures. If quantum gravity replaces the singularity with some exotic but compact object, a gravistar, a wormhole remnant, a fuzzball, then astrophysical observations might eventually distinguish such objects from classical black holes by their interactions with infalling matter or their late-time gravitational wave signals. Many of these possibilities are still on the speculative side, but the rapid advance of observational astronomy means we may not be limited to thought experiments forever. It's worth pausing on a few thought experiments that illustrate just how extreme the interior of a black hole can be in classical GR. Imagine falling into a non-rotating black hole. You would cross the horizon and continue inward inexorably toward the center. Inside, every possible future-directed path leads to the singularity. There is no way to remain at a constant radius or to escape outward. The singularity is not a place in space but a moment in your future. Your proper time, the time you experience to reach that central point, is finite. In a rotating black hole, the geometry is richer. The singularity can take the form of a ring, and the interior contains regions with strange causal properties, including the possibility, in the exact mathematical solutions, of entering other universes. Most researchers suspect that these exotic passages are artifacts of idealized solutions, and that realistic collapse would clot things up with turbulence and matter, or that quantum effects would prevent such extensions. The road toward a full quantum theory of gravity remains long and uncertain, but the project is informed by theoretical and observational guideposts. The singularity problem is not purely abstract. It motivates experimental probes, from gravitational wave observatories to black hole imaging, from particle accelerators looking for microscopic remnants to cosmological measurements. And it drives theoretical innovation. Whether the final picture involves fuzzballs, Planck stars, quantum bounces, or something entirely new, one thing is clear. Singularities are where our current understanding stops and where new ideas must begin. So when we talk about matter compressed to its limit, we're really talking about thresholds. Different physical mechanisms resist compression: thermal pressure, electron degeneracy, neutron degeneracy, and nuclear forces. Each mechanism has a scale at which it gives out, and beyond that, gravity can win in the classical picture. Where gravity dominates so strongly that spacetime bends without bound is where the notion of a singularity arises. But a singularity is best thought of as an alarm bell in the equations, a signpost pointing to the need for new, deeper physics. For the curious mind, there are a few concrete directions to watch in the near future. One is improving gravitational wave detectors. Better sensitivity, broader frequency coverage, and more detections will sharpen our understanding of the ring-down phase and may reveal subtle signatures of new physics. Another is longer baseline and higher frequency interferometry for black hole imaging, which could show finer details of the accretion flow, and the shadow, testing predictions of GR and alternative models. Laboratory analogs of black holes, systems in fluids, superfluids, or optical media that mimic some aspects of black hole horizons, can test Hawking-like processes in controlled settings, though they don't recreate gravity itself. On the theoretical side, continued development of quantum gravity frameworks and their testable consequences remains essential. Finally, it helps to remember that singularities are not a failure of science so much as a hinge in its progress. When Newtonian mechanics couldn't account for the orbit of Mercury, that mismatch pointed the way toward general relativity. When classical electrodynamics met ultraviolet catastrophes, quantum mechanics emerged. Similarly, singularities in relativity are where the current theory makes a clear prediction that signals its own incompleteness. The study of gravitational collapse and singularities thus serves a dual purpose. It tells us about some of the most extreme objects in the universe, and it points the way toward the next revolution in physics. If you like the sense of mystery here, take comfort in the fact that we actually have a lot of experimental evidence suggesting the broad brushstrokes of this picture are right. Gravity really does bend light, black holes really do exist, and relativistic collapse is an astrophysical reality. The unknowns lie deeper: the exact nature of the interior, how information behaves, and what replaces the classical singularity. Those unknowns are where future discoveries, and perhaps surprises, are waiting. People often ask whether the strangest objects in the universe, black holes, could hide the beginnings of new universes. It's a vivid idea. Maybe every big black hole is a doorway to another cosmos, a new bubble of space and time budding off from the parent universe. It sounds like science fiction, but it's also a real thread of scientific thought. Over the last few decades, physicists have explored several ways that the inside of a black hole could resemble the birth of a new universe. Some approaches are grounded in classical general relativity, some come from quantum gravity, and some stitch together speculative ideas about cosmology and evolution. Let's walk through the main hypotheses, what motivates them, how they would work in broad strokes, and what the obstacles are. At the center of the standard black hole solution sits a singularity, a location where the equations predict densities and curvatures that blow up to infinity. But physicists tend to treat singularities as a sign that the theory has been stretched beyond its limits. A singularity signals we don't know what happens here, rather than infinite anything actually occurs. The idea that a black hole's interior might be a new universe can be traced to this breakdown. If general relativity gives up at the singularity, maybe quantum gravity, the yet-to-be-completed theory that merges quantum mechanics with gravity, replaces the singularity with something else, perhaps an expanding region of spacetime that looks like the Big Bang from inside. In other words, the collapse that forms a black hole could trigger a bounce and produce a new expanding cosmos hidden behind the event horizon. If true, That would mean our own Big Bang might have been the birth of a universe inside some other black hole. One broad class of models simply notes a mathematical possibility inside general relativity. The equations allow solutions where two universes are joined by a tunnel-like structure. The so-called Einstein-Rosen bridge, an early version of a wormhole. In these solutions, inside regions of Schwarzschild black holes, there is a second universe on the other side of the bridge. However, that bridge is not traversable. If you fall in, you can't go back out or send information between the universes. Importantly, the Einstein-Rosen bridge is a mathematical feature of an idealized, eternal black hole. Real black holes form when stars collapse and the interior geometry is different. So while the bridge idea hints that another region of spacetime can be mathematically attached to a black hole, it doesn't by itself give a realistic mechanism for new universe creation. To get from mathematical possibility to actual new universe requires dealing with the singularity. That's where quantum gravity ideas enter. One influential approach is loop quantum gravity, LQG. In loop quantum cosmology, a simplified application of LQG to the whole universe, the Big Bang singularity is replaced by a bounce. A prior contracting universe reaches a very high but finite density. Quantum effects become dominant, and the contraction turns into expansion. Analogously, when matter collapses to form a black hole, quantum gravity may halt the formation of a singularity, and instead trigger a bounce that creates an expanding region inside the horizon. Carlo Rovelli and Francesca Vidato suggested a related picture called the Planck star idea. The idea is that the collapsing core reaches Planck scale density, the realm where quantum gravity matters and rebounds. From the outside, this process can take an astronomically long time because of gravitational time dilation. The formation and release of the new region is hidden behind the event horizon for so long that external observers see almost nothing. From the inside, though, that rebound could look like the birth of a universe. A useful analogy is to think about what happens when you compress a gas in a piston. If you compress gently, it warms up and stays compressed. If you compress enough that new physics appears, imagine some fundamental change in behavior that prevents further compression. The gas might spring back in different ways. In quantum gravity pictures, the spring back happens because gravity itself changes character when quantum discreteness or new quantum forces become important. Instead of hitting an infinite density point, the interior switches from collapse to expansion. Another quantum-inspired route to baby universes comes from tunneling. In quantum mechanics, systems can sometimes move between classically forbidden configurations. They tunnel through a barrier. Some cosmologists have proposed that regions of space could quantum tunnel into new inflating universes. In the 1980s and 1990s, researchers like Alan Guth and others considered mechanisms where a piece of spacetime, under the right conditions and with the right energy configuration, could pinch off and become a new inflating universe. Translating that into black hole language, the intense curvature and energy near a black hole's singularity might trigger tunneling into an inflating bubble. That bubble would be causally disconnected from the parent universe. It could expand and undergo its own evolution, even developing its own set of physical constants. Lee Smolin took these ideas in a provocative direction with what he called cosmological natural selection. In Smolin's picture, universes reproduce through black holes. Each black hole births a new universe on the other side, with physical constants slightly mutated from the parent. Universes that are better at producing black holes then have more offspring. So over many generations, there could be a sort of selection pressure favoring parameters that enhance black hole production. Smolin argued this could offer an explanation for why our universe appears fine-tuned for complex structures. Maybe those parameters are simply ones that maximize black hole production. This idea is speculative and controversial. It has a whiff of Darwinian thinking applied at the scale of universes and raises hard questions about testability. But it captures an appealing logic. If universes beget universes, perhaps cosmological properties evolve. What about white holes? A white hole is the time-reversed cousin of a black hole. Stuff can exit it, but nothing can enter. In classical solutions, white holes are odd and unstable. However, some hypotheses propose that the Big Bang could be the interior of a white hole. The Big Bang would be where matter and energy emerge from a white hole region into our expanding space. If a black hole in a parent universe produced a white hole-like region in its interior, that could look like a Big Bang for the baby universe. White holes as persistent, observable objects in our universe seem unlikely, but as a conceptual tool, they help shape the idea of black hole-to-universe transitions. A more modern and mathematically nuanced twist involves quantum tunneling from a black hole to a white hole. Haggard and Ravelli argued that a black hole could quantum tunnel into a white hole, a process that would release the trapped content after a long time. For an outside observer, this process could take extraordinarily long, perhaps million or Google of years, because time outside is effectively frozen by the intense gravitational field and redshift effects. But for the interior, the transition could be rapid and appear as an explosion that seeds a new expanding region. This ties into the Planck star idea and suggests a finite lifetime for black holes beyond the slow Hawking evaporation timescale predicted semi-classically. Hawking radiation itself complicates the story. Stephen Hawking showed that black holes are not truly black. Quantum effects enable them to emit radiation, lose mass, and eventually evaporate. For astrophysical black holes, the evaporation time is absurdly long, far longer than the current age of the universe. But in principle, black holes vanish. If a black hole turns into a white hole or sprouts a baby universe, how does that interplay with Hawking radiation? Models differ. In some scenarios, the bounce happens before complete evaporation. In others, Hawking radiation is part of the external bookkeeping that preserves information even if an inside region becomes a new universe. The famous black hole information paradox. The puzzle whether information that falls into a black hole is destroyed or preserved is intimately linked to these discussions. If information can somehow pass into a baby universe, it's not lost from the multiversal ledger, but it is lost to observers in the parent universe. That raises thorny questions about what conservation of information really means. Another influential strand of thought comes out of string theory and holography. The ADS/CFT correspondence, a powerful idea from string theory, relates a gravitational theory in a volume of spacetime, ADS space, to a quantum field theory on its boundary. In the holographic picture, information about the black hole interior is encoded on the boundary degrees of freedom. That framework has helped mathematicians and physicists reframe paradoxes and sharpen ideas about the black hole interior. It doesn't directly propose baby universes, but some extensions imagine that what looks like an interior region could be reinterpreted as another set of degrees of freedom, leading some to speculate about correspondences between black holes and cosmological spacetimes. A recent provocative idea by Maldacena and Susskind, ER equals EPR, relates Einstein-Rosen bridges, wormholes, to quantum entanglement. ER equals EPR suggests that entangled pairs of particles are connected by extremely tiny wormholes. If entanglement builds up in complex ways, could that relate to connections between whole universes? ER equals EPR is far from a demonstration that black holes make baby universes, but it shows the deepening conceptual links between spacetime geometry, entanglement, and information. It's worth pointing out what makes the black hole baby universe idea attractive beyond its sci-fi appeal. First, it addresses singularities in a potentially productive way. Instead of accepting infinities that break physics, you replace them with a physically meaningful process where something new emerges. Second, it meshes with other ideas about cosmic bounces and cyclic cosmologies, where the Big Bang is not the absolute beginning but an epoch in ongoing cosmological dynamics. Third, it offers a natural mechanism to generate many universes, more than the usual multiverse pictures that rely on inflationary bubble nucleation, and with a possible path to selection effects, as in Smolin's idea. But there are serious challenges. The most practical is observational. The interior of a black hole is hidden behind an event horizon. By definition, signals can't escape to tell us what happens inside. That makes direct tests extremely hard. You can build plausible theoretical models for what happens beyond the horizon, but checking them requires indirect signatures or clever thought experiments. Some researchers hope that quantum gravity might leave imprints on Hawking radiation or on the late-time behavior of black holes that are observable. For instance, if black holes transition to white holes on timescales relevant to cosmology, there might be bursts or unusual signals as they release energy. Searching for such explosions is an active, if speculative, endeavor. Others look for subtle effects in gravitational wave signals from black hole mergers. Tiny deviations from classical predictions might reveal quantum structure near horizons. Another challenge is internal consistency. Many of the mechanisms that produce baby universes require exotic matter or violations of energy conditions that are reasonable in quantum theory, but not in classical physics. The Farhigh-Guth-Guven analysis, for example, considered whether one could create a baby universe in a lab. They concluded that in classical GR, you can't make a baby universe without somehow providing negative energy or other non-standard matter to violate the global constraints. In cosmology, such exotic conditions may arise via quantum effects, but the details are model-dependent. There are also conceptual reservations. If every black hole births a universe, what is the total accounting of energy and information? Do the universes share conserved quantities? Are physical constants passed along or reset? Smolin's cosmological natural selection answers some of this with the mutation idea. Physical constants change slightly in the birth process. But other physicists find this unsatisfying or insufficiently predictive. Testability is paramount in science, and so far the black hole universe proposals are hard to test in ways that would convince skeptics. That doesn't mean they're wrong, only that the evidence is thin. Let's look at some concrete models and their specifics, keeping things intuitive. Loop quantum gravity models predict a bounce when densities reach a threshold set by quantum discreteness. In the black hole context, the collapsing matter forms a core whose size is never exactly zero. Quantum geometry supports it. The core's pressure reverses the collapse and drives an expansion. The inside spacetime then unfolds as a new expanding region. From the inside, this transition can be similar to the Big Bang. Space begins expanding, and fields inside can inflate and produce structure. From the outside, the horizon may remain, so the parent universe doesn't see the new child emerge. This aligns with the idea that baby universes are causally disconnected rather than being a passage one could travel through. Modesto and others have developed detailed black hole solutions inspired by LQG, where the central singularity is replaced by a regular region. These regular black holes avoid infinities and provide a consistent interior geometry. Their details vary. Some have a small compact core, some have wormhole-like features. But the shared theme is that quantum gravity replaces pathological infinities with new, finite structures. Planck stars are a particular realization. The core reaches Planck density and bounces in a way that appears as a time-smeared explosion to the outside. The calculations are delicate and require assumptions about quantum gravity dynamics, but they demonstrate a physically plausible pathway from collapse to expansion. Another promising avenue is the idea of baby universes appearing through quantum tunneling in inflating backgrounds. Here the picture is that during collapse, a region of high curvature can nucleate a bubble of false vacuum, a state that drives rapid expansion, that detaches and grows. For observers inside the bubble, the rapid expansion resembles cosmological inflation and sets initial conditions like homogeneity and flatness. For external observers, the bubble is hidden within the black hole. Models of this type often rely on an inflatoned field or similar mechanism to produce inflation inside the new region. If such fields are generic in high-energy physics, then black hole interiors become natural spots for new inflationary bubbles. Historically, the idea that our universe could be the interior of a black hole has been explored by various authors. People like Poplawski have explored spinning black holes and torsion in spacetime, suggesting that fermion spin and torsion prevent singularities and produce bounces that spawn new universes. These torsion-based bounces yield a scenario where gravitational collapse triggers particle production and rebound, forming an expanding region that could be our universe. Different authors emphasize different microscopic mechanisms: torsion, quantum geometry, stringy modifications of gravity, but the qualitative picture is shared. Singularity avoided, bounce occurs, and an interior expanding universe is born. There are interesting implications for cosmic puzzles like the arrow of time. Our universe has a thermodynamic arrow. Entropy increases over time. If the Big Bang were a bounce inside a black hole, how does that set the initial low entropy condition needed for the arrow? Some proposals suggest that the bounce naturally produces a low entropy starting point for the baby universe, because the parent black hole's collapse organizes matter in ways that lower coarse-grained entropy for the interior degrees of freedom. Others argue that entropy is not a problem because the baby universe's initial conditions are simply decoupled from the parent's thermodynamics. This remains an unsettled and active area of conceptual investigation. What about observational prospects? Most of these ideas are difficult to confirm directly, but physicists have thought creatively about signals. One possibility is that evaporating black holes, particularly small primordial black holes that might have formed in the early universe, could end their life in an energetic release that differs from the gradual Hawking evaporation picture if a bounce or black-to-white transition occurs. If such explosions occur in our cosmic neighborhood, they might show up as gamma-ray bursts or other transient signals. Searches for exotic transient events can thus constrain models, though the non-detection of such events so far only sets bounds, not definitive refutations. Another possible signature is in cosmological observables. If our universe were born inside a black hole, some models predict specific curvature signatures or statistical anomalies in the cosmic microwave background. For instance, some versions might prefer particular spatial curvature, positive or negative, while others might subtly alter inflationary predictions. Comparing these predictions with precision cosmological data can test the compatibility of certain baby universe scenarios with observed reality. So far, mainstream cosmology, with its near-flat spatial geometry and specific inflationary predictions, doesn't require a black hole origin and generally fits the data well. But the data still leave room for alternative histories, especially those that reproduce the standard inflationary outcomes for observable modes while differing elsewhere. A fascinating philosophical twist is how these ideas change the meaning of universe. If there is a hierarchy of universes connected by black hole births, the notion of a single isolated cosmos disappears. Instead, our observable universe becomes a region within a larger web of causally disconnected pockets. It raises questions about conservation laws and initial conditions. What might be constants in one universe become variable across an ensemble? For some theorists, this theoretical richness is a virtue. It offers a generative mechanism for variety. For others, it's too speculative and lacks the hard predictions needed for reliable science. It's helpful to keep the landscape clear. Some approaches maintain strict causal disconnection between parent and child universes, meaning that no signal or matter can pass back and forth. Others imagine more exotic networked relationships. Most physically motivated models fall into the disconnection camp because the event horizon prevents return. So if your neighbor's black hole made a baby universe, you wouldn't get a postcard. The baby universe would have its own space-time and internal observers, who might, in principle, reason that they evolved from a high-density past just like we do. They could then ask whether their baby universes could store records of their parents' physical constants. That's speculative, but if constants do change in the birth process, a chain of universes could explore different values across generations. How is the scientific community reacting? There's a mix of enthusiasm, skepticism, and curiosity. Some researchers pursue technical studies of regular black hole solutions and quantum bounces, trying to derive concrete predictions and identify observational tests. Others focus on foundational work, how to formulate quantum gravity consistently so these ideas can be assessed rigorously. And many are cautious, reminding us that imaginative hypotheses must ultimately face experimental or observational scrutiny. In the best cases, speculation drives new calculations and experiments that refine or discard hypotheses. That's how science progresses. If you'd like a quick checklist of the main hypotheses and their core claims. 1. Classical wormhole/Einstein-Rosen bridge mathematical connections between regions of spacetime, but not realistic for formed black holes. 2. Loop quantum gravity bounces and Planck stars. Quantum geometry halts collapse and creates an expanding region that can be interpreted as a baby universe. 3. Tunneling to inflating bubbles, strong curvature induces a quantum nucleation of an inflating region inside the black hole. 4. White hole/black-to-white transition. Quantum processes turn black holes into white holes that seed new universes. 5. Cosmological natural selection. Universes reproduce through black holes with slight variations in constants, leading to selection effects. Each has supportive arguments and each has weak points. One important practical takeaway is that progress depends strongly on advances in quantum gravity and on clever observational strategies. For example, if we ever detect primordial black holes evaporating or discover anomalies in gravitational wave signals that can't be explained by classical general relativity, that could point to new physics near black hole horizons. If we can measure features of cosmic inflation with greater precision and find inconsistencies with standard inflationary models, that could open a window to alternative origin stories like baby universes. Until then, the idea remains an intriguing theoretical possibility grounded in serious physics, but not yet established. There is also educational value in exploring these ideas. They force us to confront what we mean by beginning, boundary, and origin in physical terms. The Big Bang is often described as the start of spacetime, but that phrasing hides all sorts of assumptions. If the Big Bang is instead a local event inside a larger spacetime, then beginning is relative, not absolute. That conceptual flexibility is useful because it prevents us from confusing mathematical extrapolation, the classical singularity, with physical reality. Finally, the story reminds us of a larger scientific truth. When equations break down, something interesting is usually happening. Singularities prompted decades of deep theoretical work on black hole thermodynamics, on quantum field theory in curved spacetime, and on quantum gravity. The notion that black holes might be cosmic wombs for baby universes is a dramatic, appealing way to frame the kinds of questions physicists are asking at the frontier. Whether nature actually behaves that way remains an open question, but the pursuit has already enriched our understanding of gravity, quantum mechanics, and cosmology. So, could the interior of a black hole resemble the birth of a new universe? The short, cautious answer is possibly, according to some well-motivated theoretical frameworks. The long answer is richer and more conditional. Several credible routes from collapse to expansion have been proposed, grounded in quantum gravity, tunneling physics, and cosmological models. They face significant conceptual and observational hurdles, but exploring them sharpens our tools and clarifies what a complete theory of spacetime and matter will need to explain. The possibility is fascinating not simply because it's dramatic, but because it connects deep puzzles, singularities, the origin of the universe, the fate of information, in a way that invites concrete calculation and, eventually, empirical test. Until then, the idea remains an elegant possibility at the boundary between what we know and what we're still figuring out. Imagine for a moment that the Big Bang, the moment when our universe was unimaginably hot, dense, and rapidly expanding, wasn't the absolute beginning of everything, but the beginning of our universe's history inside a much larger story. Picture our universe as the inside of a bubble that formed when something collapsed in a different cosmic backyard. That something could be the core of a black hole in another universe. The idea sounds wild, but it's grounded in real physics questions and a few thoughtful proposals that try to connect what we know about black holes and what we know about the Big Bang. So what if the inside of a black hole doesn't end in an unreachable, infinitely small point, but transitions into a new region of spacetime that expands, effectively creating a new universe? From the outside, the parent universe still sees a black hole, but the interior could be the seed of a whole new cosmos. To someone living inside that new cosmos, that would be us in this picture, the early hot, dense, expanding conditions would look like our Big Bang. This is not just fanciful metaphysics. Several physicists have sketched mechanisms by which gravitational collapse in a parent universe could avoid a singularity and instead produce a bounce or a new expanding region. One influential idea comes from work on quantum gravity and on ways to modify or extend general relativity at very high densities. For example, the Einstein-Cartan theory adds a little extra geometry, called torsion, that becomes important when particle spins are packed extremely tightly. At ordinary densities, torsion is negligible, but at the ultra-high densities you'd find near a classical singularity, it can provide a repulsive effect that stops collapse before a singularity forms. The result can be a bounce that, in the coordinates of the parent universe, looks like the formation of a black hole, while inside it looks like the birth of a new expanding region, a baby universe. Another route comes from approaches to quantum gravity like loop quantum gravity, where space itself is thought to be made of discrete chunks. In certain calculations, the crushing collapse inside a black hole reaches a threshold where quantum geometry pushes back, again replacing an inevitable singularity with a bounce and an expanding interior. The technical details differ between proposals, but the common intuition is that the physics that halts the formation of a true singularity could naturally produce conditions like those of an early, hot universe. Why does this matter? For one thing, it gives a possible explanation for the effective start of our universe without demanding absolute creation from nothing. If a bounce inside a black hole is possible, then our Big Bang could be the inside story of such a process. It recasts the Big Bang from being a boundary of everything to being a local event inside a larger space-time, like a bubble forming inside a larger foam. To make the idea digestible, here's a helpful everyday analogy. Imagine a soap bubble forming as you dip a wand into the soapy film and lift it from the surface. From the outside, a thin neck pinches and separates a new bubble from the soap film. To an ant living on the bubble's surface, the formation might seem like the beginning of its world. The soap film outside the bubble continues, and the bubble is part of a larger system. A similar conceptual move is at play with the black hole as universe idea. From the outside, the parent universe, you see a collapsing region forming a black hole. From the inside, you experience an expanding universe that starts small and grows. There are several interesting consequences and questions that come with this possibility. First, causality and horizons. When matter collapses to form a black hole, it creates an event horizon, which prevents signals from the inside from reaching the outside. That means the interior is causally disconnected from the parent universe. Information inside can't come back out. For observers in the parent universe, the black hole is a one-way street. But inmates of the baby universe don't notice that boundary as an edge of space. They simply experience expanding space on all sides. The causal disconnect explains why, even if we were born inside a black hole in some parent universe, we wouldn't have any direct way of looking back and checking what that parent looked like. The parent remains forever hidden beyond the horizon. Second, what about the appearance of the Big Bang itself? In our standard cosmology, the Big Bang is often described as a singular start point, and this is tied to the mathematical limits of general relativity. In black hole baby universe scenarios, the Big Bang is instead a bridge or a bounce. The extremely hot, dense early universe is the aftermath of that bounce. Because different coordinate choices can make the same spacetime look like a singularity or a regular bounce, it's easy to get lost in the technicalities, but the key point is conceptual. Our early universe could be the internal side of a gravitational collapse event, not an absolute beginning. Third, how does this idea sit with inflation, the rapid stretching of space thought to have occurred fractions of a second after the Big Bang? Some black hole as origin models include inflation as a subsequent phase inside the baby universe. That makes sense because inflation helps explain the observed flatness and uniformity of our universe. If the infant universe created by a bounce also goes through a period of exponential expansion, for reasons that depend on the details of particle physics or quantum gravity, it could iron out irregularities and produce the cosmic microwave background, CMB, patterns we observe. Other proposals try to explain the observed large-scale features without inflation, but those are trickier to match to the detailed measurements. In short, most realistic proposals for a universe born inside a black hole accommodate or reproduce something like inflation. Fourth, what empirical evidence could support or refute the idea? This is the tough part. By construction, the baby universe is hidden behind an event horizon. No signals can cross it. That limits the direct observational tests a lot. Nonetheless, physicists have thought of indirect signatures that might be detectable. For example, if the parent black hole had angular momentum, which most astrophysical black holes do, that rotation could leave an imprint on the baby universe. One set of proposals suggests that a rotating collapse could produce a baby universe with a preferred direction or slight twisting. If that directionality translated into subtle asymmetries in the cosmic microwave background, patterns that break perfect isotropy, we might find evidence for such a twist in careful CMB measurements. People have searched for unexpected alignments or large-scale anomalies in the CMB. Some oddities have been reported, but none rise decisively above the level of statistical flukes yet. It's an area of active data analysis and heated debate. Another possible signature involves the values of the physical constants. If baby universes inherit values of parameters in a way that depends on the details of the parent's collapse, then a population of universes might explore different constants. Some scientists, like Lee Smolin, have suggested a kind of cosmological natural selection. Universes that produce many black holes would tend to spawn many offspring, so parameters that make black hole production easier would become more common. That leads to testable hypotheses. If our universe's constants seem tuned to maximize black hole production, That would be consistent with Smolin's idea. People have scrutinized this claim and tested it against what we know about stars, neutron stars, and nucleosynthesis. Results are mixed, and the arguments involve complicated astrophysical modeling. It's an intriguing line of thought because it offers at least a potential route to observational consequences. There are also theoretical challenges that any viable black hole origin model must face. The most obvious is that we need a good theory of quantum gravity to describe what happens at Planck scale densities. General relativity alone breaks down at singularities, so any claim that collapse turns into expansion needs an account of the microphysics that makes that happen. Different quantum gravity programs offer different possibilities. Some produce bounces, others lead to fuzzballs or other exotic outcomes. Until we have experimental data that constrain quantum gravity, we remain in the realm of plausible ideas rather than tested facts. Another challenge is entropy and the arrow of time. Our universe has low entropy at early times, which underpins the directionality of time, why entropy increases going forward. If our universe started as the inside of a black hole, the question becomes, how did the baby universe begin in such a special low-entropy state? Some models argue that the formation mechanism naturally produces low entropy inside, while critics worry that generically a bouncing process would create high entropy, not low. Resolving this requires a careful accounting of what counts as entropy across the parent-child divide, and that's an area of active philosophical and physical debate. There's also the issue of infinite regress. If our Big Bang came from a black hole in another universe, where did that universe come from? Did it, too, arise inside a black hole in some earlier universe? The idea can create a chain of universes begetting universes, which some find appealing because it removes the need for an ultimate origin. Others object that it simply pushes the problem back. Whether an infinite chain is acceptable or problematic is partly philosophical, but from a physics standpoint, it doesn't necessarily need resolution. If the mathematical model works, the chain could be eternal or could have a deepest ancestor, depending on the dynamics. It's worth noting that the black hole as baby universe idea sits in a family of proposals that try to explain our cosmos without positing creation from absolutely nothing. Other proposals include the cyclic ekpyrotic model, where two branes in higher dimensions collide periodically causing Big Bang-like events, and conformal cyclic cosmology, where each eon's infinite future sets up the next Big Bang. The black hole proposal has the advantage of being tied to a very real, observed phenomenon, black holes, so it feels less speculative in some ways than invoking entirely new entities. Still, linking black holes to cosmogenesis demands new physics in the strong gravity regime, so it remains speculative too. Now, let's make the physics behind the inside of a black hole picture a little more intuitive without getting lost in equations. Think of space-time as a flexible fabric. In most everyday situations, that fabric is smooth and gently curved by planets and stars. In a collapsing star, the curvature becomes extreme and the fabric pinches down. General relativity suggests the pinch goes on to a point of infinite curvature. This is the singularity. But imagine that at the smallest scales, the fabric isn't infinitely stretchable. Instead, its microscopic structure resists being compressed beyond a certain threshold. When the fabric reaches that threshold, it snaps into a new configuration that releases pressure in the form of an expanding region. From the outside, the pinch still looks like a black hole. From the inside, the snapped fabric looks like expanding space, our Big Bang. This snapping analogy is crude, but it captures the essential picture. New physics at extreme densities transforms collapse into expansion. If that is how nature behaves, then black holes are not merely endpoints, they are cosmic seeds. Another thread of thought worth mentioning revolves around the concept of baby universes and topology change in space-time. In general relativity, space-time can, in principle, have complicated structures like wormholes or branches. Under certain conditions, quantum effects might allow tiny bubbles of new space-time to detach and evolve. This is more speculative and leans on quantum cosmology tools, but it's another formal way researchers have pictured universes being born from other universes via gravitational collapse or quantum tunneling. Now for a realistic assessment. As attractive or intriguing as the idea is, we should be honest about its current status. There's no definitive observational proof that our Big Bang came from a black hole in another universe. The predictive power varies by model. Some versions make testable claims about CMB anomalies, particle physics parameters, or the distribution of black holes, while others are more conceptual. The cosmic microwave background and the distribution of galaxies provide extraordinarily precise information about the early universe, and any successful model must reproduce those observations. Many black hole origin proposals can, with the right assumptions, be made compatible with what we see. But that's different from making a unique prediction that would clearly favor the idea. Thinking about this idea also brings up a beautiful conceptual twist. Black holes and big bangs, which at face value seem like opposites, one swallows everything, the other releases everything, might actually be two sides of the same coin when considered from different perspectives. For an outside observer, a black hole is an inescapable trap. For an inside observer, the very same process could be the birthing of space. Let's take a slightly different angle and consider what this picture implies for cosmological fine-tuning. Physicists often marvel at how certain constants of nature, like the strength of forces or masses of particles, seem finely tuned to allow stars, chemistry, and life. If universes reproduce through black holes and the reproduction mechanism slightly tweaks physical constants randomly or according to some rule, then an ensemble of universes would naturally show a distribution of constants. Observers would find themselves in a universe whose constants are compatible with complexity. That's a kind of selection effect. Lee Smolin's cosmological natural selection is the best-known realization of this idea. If universes that produce more black holes have more offspring, then the multiverse would be biased toward physics that produces black holes. Whether that bias would also favor life-friendly physics is a subtle question, and not one the idea guarantees. But it shows how black hole origin thinking can link to deep questions about why the universe looks the way it does. To keep the idea in perspective, it's useful to remember that physics progresses by proposing models, working out their predictions, and comparing those predictions with observations. The black hole origin picture turns a conceptual key. It connects two extreme regimes, collapse and creation, using the idea that extreme gravitational physics may produce new spacetimes. It is a hypothesis like any other, valuable if it suggests new observations or deepens understanding, but provisional until evidence supports it. What could count as evidence? One possibility is a distinctive signature in the cosmic microwave background that can't easily be explained by standard inflationary scenarios. Another is a statistically significant pattern in astrophysical data that aligns with a model's specific predictions. For instance, a distribution of neutron star masses or black hole formation rates that match the universes that reproduce well selection. A more dramatic possibility would be a theoretical breakthrough in quantum gravity that shows collapse must lead to bounce and expansion under general conditions. That would make the scenario much more compelling, even without direct observational contact with a parent universe. There's also an educational and psychological value to this idea. It pushes us to think broadly about what beginning might mean, and to challenge the assumption that the Big Bang must be a unique, absolute origin. It encourages cross-pollination between astrophysics, quantum gravity, and cosmology. Even if future data ultimately rule out baby universes born inside black holes, the work done exploring the idea helps sharpen our questions and methods. Finally, let's touch on a human dimension. There's something deeply appealing about a model that gives black holes a creative role. In popular culture, black holes are often portrayed as annihilating monsters. The baby universe idea flips that. Black holes could be cosmic parents, each potentially a cradle for new universes. It's an image that satisfies an intuitive craving to see continuity rather than abrupt absolute beginnings. Scientists aren't motivated by metaphor alone, of course, but such images help the public and researchers alike to frame the questions in stimulating ways. In the end, the suggestion that our Big Bang emerged from matter collapsing in another universe is a fascinating possibility that sits at the frontier of our understanding. It bridges observational astrophysics, black holes we can see in galaxies and gravitational wave detectors, with speculative but serious theoretical work on extreme gravity and quantum effects. It raises profound questions about origins, causality, and the nature of physical law. It also points squarely to the need for a better theory of quantum gravity and more precise cosmological measurements. Whether or not the idea turns out to be correct, it's a perfect example of how scientific imagination, constrained by what we know and open to what we don't yet know, can propose surprising links between seemingly disconnected phenomena. Black holes and Big Bangs are both extremes of gravity, and exploring how they might relate is one of the ways physics probes reality's most extreme corners. So next time you read about a black hole swallowing a star or a new paper on the early universe, keep in mind that on the cosmic scale, endings and beginnings might be much more entangled than they first appear. One of the big challenges in the idea that universes could form inside black holes is that, from our point of view, the black hole interior is hidden behind an event horizon. That means even if something dramatic, a bounce that spawns a new expanding region, happens deep inside, we can't reach in and see it directly. It's like someone telling you there's a doorway hidden inside a locked house that leads to another world. You can study the outside of the house all you like, but you can't walk through that door unless the rules of the house change. So the immediate question scientists face is, how do you test a theory whose key events are causally disconnected from us? This brings us to the first big category of unanswered questions. What physical principles govern what happens at the core of a black hole? General relativity, Einstein's theory that describes gravity, predicts that matter collapsing under gravity forms a singularity, a point of infinite density and zero volume. That singularity is a mathematical signpost that our equations have broken down. Physics, as described by classical general relativity, stops making sense there. Most physicists expect that once quantum effects are included, singularities will be resolved. The infinite density is an artifact of pushing a classical theory beyond its domain. Different approaches to quantum gravity give different pictures of what replaces the singularity. Some, like certain versions of loop quantum gravity, suggest a quantum bounce. The collapse reaches a maximum density and then transitions into a new expanding region. Some string theory-inspired ideas and others point toward more exotic outcomes, like a fuzzball replacing the interior so there is no conventional horizon, or complicated topological processes that create separate spacetime regions. Each of these possibilities carries a different implication for the baby universe idea. If a bounce produces a new, expanding spacetime region that pinches off from ours, you can say a universe was born inside the black hole. If instead the interior is a complicated, horizonless object, or if information is somehow fully encoded in Hawking radiation, then the story is different. Because the theories differ, a major unsolved problem is simply pinning down which theory of quantum gravity is correct. We don't yet have an experimentally confirmed quantum theory of gravity, and that makes deciding between these scenarios hard. That lack of a settled theory leads to a second big question. Even if a new universe were created inside a black hole, how would its birth influence observable properties of the parent universe? In many proposed pictures, the new universe becomes causally disconnected. It can't send signals back to the parent universe. If that's true, the child universe is effectively untestable from the parent, which looks like a dead end for empirical science. Still, scientists look for indirect ways that the idea might leave traces we can detect. One way is to consider whether the process that creates baby universes could affect things outside black holes in subtle ways. For instance, if quantum gravity modifies the way black holes form or evaporate, those modifications might slightly change the black hole's exterior behavior. Think of two clocks hidden behind doors. If the hidden clock gains or loses a second for some reason, that change might slightly shift the pattern of sounds you hear outside. In black hole physics, this could translate into tiny deviations from the predictions of classical general relativity in how a black hole's shadow looks, how it rings after being disturbed, or in the detailed spectrum of radiation it emits as it evaporates. Astronomers are starting to probe those possibilities. The Event Horizon Telescope gave us the first real image of a black hole's shadow. That's a gross, big-picture test of strong gravity near a horizon. It confirmed that, within observational error, the size and shape of the shadow match what Einstein's theory predicts. That rules out a broad class of exotic alternatives that would produce a dramatic mismatch. Gravitational wave detectors like LIGO and Virgo have begun to listen to black holes merging. And the ringdown phase, the way the merged object settles down, is an arena where small deviations from general relativity might show up. Some theorists have proposed that if horizons are replaced by exotic structures, these mergers should produce echoes in the gravitational wave signal. Faint, repeating bumps after the main ringdown. Searches for echoes have been performed, with intriguing hints here and there, but no consensus detection yet. So these observational programs are starting to chip away at the question, but they haven't delivered anything that unequivocally supports the baby universe picture. A third unresolved issue ties into what drives the physical constants and initial conditions of universes. Lee Smolin famously proposed a version of black hole cosmology called cosmological natural selection. The idea that each black hole might spawn a daughter universe with slightly different fundamental constants, and that universes that happen to have constants favoring black hole formation would produce more children and therefore dominate the population. It's an attractive, Darwinian-sounding idea because it could, in principle, explain why our universe's constants appear well-suited for complex structures. But it raises several questions. First, does the mechanism that creates a baby universe actually change those constants? And if so, in what way? Second, can we check whether our universe's constants are indeed tuned to maximize black hole production, or whether they are tuned for other reasons, like producing chemistry in stars? These are tricky to pin down because we need a way to evaluate nearby universes with slightly shifted constants, a theoretical, computational exercise rather than an observational one. Some partial checks have been attempted. For example, varying constants in computer models to see how many black holes would form. Those studies show that changing some constants could reduce black hole formation, but the results are model-dependent and not decisive. Another pathway scientists consider is searching for imprints in cosmological data that might be characteristic of certain bounce scenarios. If our own universe began from a bounce rather than a singular Big Bang, that bounce might have left a specific signature in the pattern of cosmic microwave background, CMB, fluctuations, or in the spectrum of primordial gravitational waves. The CMB is a snapshot of the universe when it was about 380,000 years old, and its tiny irregularities carry a record of what happened much earlier. Certain bounce models predict particular types of non-Gaussianities, deviations from the simple random patterns predicted by standard inflationary cosmology, or a different shape of the primordial gravitational wave spectrum. Future missions, more sensitive satellite surveys of the microwave sky, and new gravitational wave detectors might be able to test these predictions. But the problem is that many different theories can be tuned to produce similar observable effects. So even if we see an anomaly, connecting it uniquely to baby universe creation inside black holes is hard. There's also the deep question of information. In the 1970s, Stephen Hawking showed that black holes evaporate via quantum processes, emitting what we call Hawking radiation. That process seemed to lead to information loss. The information about what fell into the black hole would be irretrievably lost when the black hole evaporated. That outcome conflicts with a central principle of quantum mechanics. That information is conserved. Over decades, a lively debate formed around this so-called black hole information paradox. If black holes spawn new universes, one might imagine the information simply carrying over into the child universe, problem solved. But this resolution has a catch. It effectively hides the information in a region we can't access, which some physicists find unsatisfactory because it doesn't restore information to the Hilbert space of the parent universe. From an observational standpoint, whether information is preserved or lost matters. If information is preserved and eventually encoded in Hawking radiation, then the detailed spectrum and correlations of that radiation should, in principle, contain signatures that differ from a perfectly thermal emission. People have tried to understand whether subtle correlations in Hawking radiation could be measured. In practice, detecting Hawking radiation from astrophysical black holes is hopelessly tiny, and any future detection is likely to come from smaller, evaporating primordial black holes or hypothetical micro-black holes, neither of which we have confirmed exist. That leads to another set of open questions about primordial black holes and black hole remnants. If black holes create universes and the process leaves behind Planck-scale remnants, those remnants might be stable and could contribute to dark matter. Alternatively, primordial black holes formed in the very early universe, are interesting because their abundance is constrained by a range of astrophysical observations, microlensing surveys, CMB distortions, gravitational wave detections, etc. These constraints provide limits on how many primordial black holes could exist, which in turn constrains some scenarios in which baby universes might play a cosmological role. On the other hand, if we did discover a population of primordial black holes, or found a signature of microscopic evaporating black holes, that would open up entirely new ways to test quantum gravity ideas, including baby universe scenarios. A related practical question is whether there are any experimental or observational setups that could more directly probe the relevant physics. Some researchers have examined whether high-energy experiments, like particle colliders, could create tiny black holes, and whether those tiny black holes might seed baby universes. In theories with extra-spatial dimensions, the energy threshold for black hole creation can be much lower, making this a real possibility in principle. The Large Hadron Collider has not seen any sign of such tiny black holes, and current consensus is that it's unlikely that colliders will create them. Even if they did, the same issue of causal separation remains. Any newly formed microscopic black hole would evaporate extremely quickly, and evidence for a daughter universe wouldn't be directly observable in our detectors. There's a different theoretical route that some physicists explore. Use the mathematical consistency and internal predictions of advanced quantum gravity frameworks to decide whether baby universes are natural or likely. For example, the ADS/CFT correspondence, a powerful duality discovered in string theory, relates a gravitational theory in a bulk space to a quantum field theory on its boundary. In that context, questions about what happens inside a black hole map to questions about the unitary evolution of the boundary theory. Some hopeful theorists imagine that if a boundary theory can be shown to be fully unitary and consistent, it may tell us whether black holes can branch off baby universes, or whether they must return their information to the parent through intricate correlations in emitted radiation. But this approach is mathematically challenging and primarily applies to specific kinds of idealized spacetimes, such as those with negative cosmological constant, the AdS case. So its direct implications for our universe, which appears to have a tiny positive cosmological constant, are not straightforward. A further complication is that creating testable predictions often requires concrete, computable models. Many of the baby universe ideas are qualitative. The singularity is replaced by a bounce, and a new region expands. Translating that into a precise prediction about a measurable quantity, like a subtle pattern in the CMB or a measurable shift in gravitational wave ringed-on frequencies, is technically demanding and often depends on choices of parameters. That opens the door to the charge that the idea is too flexible. It can be adapted to match a range of observations, which weakens its predictive power. Scientists are rightly skeptical of models that can't be pinned down and use that as a criterion for judging which theories are worth pursuing. Nevertheless, there are specific, more concrete signatures that people keep an eye out for. One is the ring-down and echo signature in gravitational waves already mentioned. If horizonless alternatives or quantum modifications near the would-be horizon exist, they may reflect part of the gravitational wave back and lead to echoes. Those echoes would be faint and require careful data analysis and better detectors. But the next generation of observatories, the planned Einstein telescope or cosmic explorer, could significantly improve our sensitivity. Another potential observable is a distortion in the high-frequency gravitational wave background produced in the very early universe. Some bounce models predict an enhanced or suppressed spectrum at certain frequencies. If future detectors like LISA, DECIGO, or ground-based detectors operating at different frequency bands can chart that primordial gravitational wave background with enough precision, we might either find support for bounce scenarios or rule out specific classes of them. On the electromagnetic side, precise tests of black hole shadows could constrain exotic alternatives that would make black holes significantly different from the classical Kerr solution, predicted by general relativity. The next generation event horizon telescope observations, including longer baselines and better imaging algorithms, will refine those constraints. Additionally, studying the dynamics of matter near the innermost stable circular orbit, the last stable orbit before material plunges into a black hole, with X-ray timing and spectroscopy, can probe the strong gravity region and might reveal deviations from classical expectations. There are also indirect cosmological tests. If Smolin-style cosmological natural selection were true, then universes with parameters that maximize black hole production should be common. That leads to some testable ideas. If small changes to constants increase black hole production, then our constants wouldn't be at a local maximum. The challenge is that evaluating that requires an enormous theoretical and computational effort to see how cosmic evolution changes as you tweak constants. Moreover, life-friendly universes are a narrow subset of parameter space, and selection effects, we are here to observe, complicate the interpretation. Still, this approach has the advantage that it turns a speculative idea into something one can, at least in principle, confront with calculation. One of the more subtle, conceptual unanswered questions is how conservation laws behave across baby universe creation. Energy conservation in general relativity is already a nuanced topic because there's no global, coordinate-independent definition of energy in an expanding universe. If a baby universe pinches off, does it take energy with it? Does total energy get redefined? What happens to charge conservation or baryon number? Some proposals allow conserved charges to be retained or transmitted. Others suggest they might be effectively hidden in the child. These questions matter for possible observational consequences. For instance, if forming baby universes results in quantifiable energy loss from the parent black holes beyond what classical physics predicts, that could be a signature, but the expected effects are typically minuscule. A technical but important open question is the role of topology change in spacetime. Creating a baby universe can be thought of as a change in topology. The geometry evolves so that a new handle or branch appears. In classical general relativity, topology change is heavily constrained and often leads to singular behavior. Quantum gravity might allow topology change more naturally, but understanding how and when this happens is mathematically complex. Progress here requires deep work in mathematical physics and quantum field theory in curved spacetime. Finally, there is the question of whether the baby universe hypothesis is the best way to address some of the big puzzles in cosmology and fundamental physics. For example, the cosmological constant problem, why the vacuum energy density is so small but non-zero, has tempted theorists to invoke anthropic arguments in a multiverse. Baby universe production is one mechanism that could populate a multiverse, but it's not the only one. So scientists ask, does the baby universe route offer clear advantages or new testable predictions compared with alternatives like eternal inflation or string theory landscapes? That comparison is ongoing and depends heavily on whichever theoretical framework gives us the most coherent, computable outcome. What would count as convincing evidence then? It helps to think in tiers. The strongest kind of evidence would be a direct, unique signature predicted by a specific, well-developed quantum gravity model that distinguishes baby universe creation from other possible explanations. And that signature would be observed in multiple, independent ways. For instance, suppose a concrete theory predicts a precise pattern of echoes in gravitational waves and a specific tweak to black hole shadows and a matching non-Gaussian feature in the CMB, and all three are seen as predicted. That would be powerful, but we are far from that level of maturity in both theory and observation. A more realistic near-term outcome is incremental, ruling out classes of models, tightening constraints, and finding anomalies that push theorists toward particular frameworks. If gravitational wave data never shows echoes, that will disfavor some horizonless or highly non-classical scenarios. If EHT continues to see shadows that align with classical black holes to very high precision, that constrains modifications near the horizon. If searches for Planck mass remnants or primordial black hole evaporation signatures come up empty, that tightens bounds on scenarios that rely on those features. Another plausible route to progress would be a breakthrough in theoretical physics that narrows the space of viable quantum gravity models. If one approach becomes strongly favored, for instance, by producing clear predictions that match unrelated observations, and that approach predicts baby universe creation as a generic outcome, then the baby universe idea would gain credibility even if direct observational proof remained elusive. In other words, convergence between theory and the small but growing set of precise observational constraints could make the idea much more compelling. In the meantime, the debate is healthy because it forces us to sharpen questions about what we can measure and what we can hope to infer. It's an exercise in scientific humility. Some ideas are elegantly speculative but may be forever out of reach observationally, while others produce testable consequences. The practice of science moves forward when the community turns speculation into concrete models that can be falsified or supported. So what should a curious, non-specialist take away from this? First, the idea that universes might form inside black holes is scientifically serious. It's not pure science fiction, because it arises naturally in several candidate theories of physics that attempt to reconcile quantum mechanics with gravity. Second, it's a hard idea to test directly because of causal separation, but it might leave indirect fingerprints on observables like gravitational waves, black hole shadows, or cosmological data. Third, progress depends on both better observations, more sensitive detectors across different messengers, gravitational waves, electromagnetic signals, and perhaps neutrinos and cosmic rays, and better theory, concrete, predictive quantum gravity models. Finally, we should expect many partial answers before any definitive verdict. Models will be constrained, some will be ruled out, and new surprises may emerge. The unanswered questions are not just technical, they're philosophical too. What does it mean to explain the values of the constants in our universe? Is a multiverse populated by baby universes a scientific explanation, or an unfalsifiable metaphysical idea? What counts as evidence when causal contact is absent? These are debates that touch the limits of empirical science and are therefore healthy and necessary. And yet, there's an exciting experimental landscape emerging. Gravitational wave astronomy is in its infancy, but already revolutionizing how we study black holes. Improved detectors in the coming decades will open wide frequency bands and signal sensitivities we can only imagine now. Radio, X-ray, and millimeter observatories will sharpen images of black hole environments. Cosmologists are planning new surveys and probes that will measure the CMB and large-scale structure with extraordinary precision. All of these will create tighter fences around theoretical speculation. If baby universe models leave any observable trails, even faint ones, the next 2 or 3 decades of observational astronomy have a chance to find them. In the end, the idea that black holes might be seeds of new universes sits at the crossroads of the deepest questions we can ask. How does spacetime behave at its most extreme? How do the laws of physics arise, and can they vary? Are we part of a larger ensemble of universes, and does that ensemble have a dynamical rule like natural selection? These questions push against the boundaries of what we can measure, but they also guide the development of new instruments, new theories, and new ways of thinking. Whether or not universes inside black holes turn out to be real, the attempt to answer that question will teach us a great deal about gravity, quantum mechanics, and the cosmos. So keep an eye on those gravitational wave catalogs, the new images of black hole shadows, and the increasingly precise maps of the early universe. Each of those datasets is a piece of the puzzle. And remember, science often advances through a combination of radical ideas and rigorous skepticism. Theory gives us bold possibilities. Measurement gives us the constraints that separate the promising paths from the blind alleys. The baby universe idea is one of those bold possibilities. It faces tough questions, but it has also shaped interesting, testable lines of research. That mix, audacity guided by scrutiny, is how progress happens, and that's why physicists keep grappling with these unsolved mysteries in black hole cosmology.